Hello everyone, welcome to our tutorial. This tutorial is called Time is Precious. We all know that time is a precious resource in the real world, but today we want to investigate the importance of this resource in deep learning and to see how we can improve our methods with getting supervision from temporal information. I'm Mohammadreza and organizing this workshop with Shashanka and Yuki. A very warm welcome to all of you. We are very happy to have you here to listen to our very exciting line of speakers and learn from them. The schedule for today is that we will, at first I will discuss some important fundamental concepts of self-supervised learning and also giving some intuitions about how temporal information can bring more knowledge to the table compared to solely using images. And then Shashanka would take the stage and talk about prior works that have used temporal supervision signal to improve their tasks. And Yuki will be talking about the most recent works like time tuning and Dora that have used this concept and maybe are one of the first methods that have started this direction going towards learning strong image representations from videos. And then we will have a coffee break, and after that we will be listening to our very exciting line of researchers and scientists. For instance, Zhao is from Google DeepMind. He has been working on object segmentation, object reconstruction, and he has been doing a lot of video related research and has contributed to kinetics, to the famous kinetics data set, also perceiver models, and he has co-organized kinetics challenge for CVPR between 2017 to 2021, and also the perception test in the last year ECCV. And we will have Ishan, which is a research scientist in Gen AI at Meta. Previously he was at the FAIR team working on self-supervised learning methods, and personally I have learned a lot of SSL methods through his papers. And he was featured in the MIT Tech Review's 35 innovators under 35 list. And in the end we will have Emin, who was a postdoc in Rice University working on the relationship between our models, deep learning models, and the cognitive processes that are going on in the brain, and actually trying to find out whether our brain works similar to neural networks or vice versa. And also how it uses temporal information. So it's a very related task to what we do. And finally Yuki will conclude the whole tutorial and discusses the open problems and final remarks. Okay, so I would be talking about the fundamental stuff. So for the very fundamental question, let's just start from this question, which is, what are the main factors of AI progress? Okay, so AI progress, when we are talking about AI progress, we cannot ignore hardware development. So we are here, one of the reasons that we are here, let's say, is because of having very advanced and high performance hardware chips. So from here I would like to thank all the people or the hardworking hardware engineers, and because of making this possible for us. After that I want to talk about models, and I generally think that models that we have has made a very huge contribution to what we have now as high performance AI systems. Models like CNNs or transformers made it possible for us to scale our experiments and to evaluate them on larger scale and to train them on larger scale data sets. And this helps us to be sure that the underlying function that we are trying to model through the data sets is the estimated function through our models is more close to the true underlying function in the data sets. And also, in every part of my talk so far, I've used the word data set, so it's not possible to talk about AI progress without data set. And this is the function that we are trying to model through our models. And data sets such as ImageNet, or recently weakly supervised data sets such as Lion, has helped us a lot to make this huge progress in AI. And in the end, the interaction between these domains is so important, and models are designed based on the hardware-specific requirements, or data sets are designed based on the models. Models are designed based on the data set, and the interaction between these areas also help us a lot to make a contribution. Okay, so talking about data sets, let's see how can we use the data. Okay, the first one, the simplest one, is supervised way. So simply in the supervised training, you're given X and a label Y, and you're expected to learn a model which transforms an X to your label space, which is Y. For instance, if you want to detect if you're given a cat image, if your task is classification, your label is simply a cat, which is a one-hot vector. If it is an object detection task, your label could be an object bounding box, or if it is semantic segmentation, it could be so fine-grained, such as a cluster map of the whole image at the pixel level. Another way of using dataset is weakly supervised training. Another way of using our data is weakly supervised training, in which you are given X and a label Y, but the label Y is not directly related to the task you want to solve. For instance, it's a caption of the image, and you're asked to learn some useful high-level features from this information so that it can even be used further in other tasks such as classification or object detection or segmentation, but the label that you are provided with is not exactly tailored for your downstream or for your specific target task. But researchers soon realized that there are some issues with these approaches. The first issue is that supervised or weakly supervised data are not very scalable. If you look at the amount of data we have on the internet everywhere, the amount of supervised data and weakly supervised data are much lower than the raw data, which is the unlabeled data available on the internet. So this makes it a bit harder for us to scale our models, and we know that we have achieved to this AI progress because of scalability, because of also we have some theoretical bounds for that. Yeah, if we have more data, if we can train our models with a lot of data, then we can even, using those loose theoretical bounds, maybe we can even show that the function that we are trying to model, the real function, and the function that we are trying to estimate are closer to each other. But so scalability is very important, but for supervised and weakly supervised setup, we cannot scale as well as the on-label setup, which is using only raw data, only raw data. And the other one is that, okay, labels have also the problem of cost of relabeling. For instance, if you created a data set for Super Mario character in 1981, you had some pixelated images for the appearance of this animation character, let's say, but over the time, this the appearance has developed to something very high definition and very beautiful, like a 3D animation. And now your models need to be retrained again with these kinds of new appearance, which adds some challenges, because you need to then maybe forget the previous information and add new information, and all this stuff may cause some training difficulty for the model. Another problem is that sometimes labels have some inherent problems. For instance, if you ask people to give you the picture of their houses, and depending on where they live, they may give you different images. But if you train a model to distinguish all these images as house, it might be hard to extract something shared, a function that works in shared between all these different samples that we have from our data set. The reason why it happens is that sometimes the information doesn't exist in the image. So people call something a house because they have some internal feelings like safety or whatever other feelings that they may have, and that's why then they come up with a label for an image and call it a house, for instance. Basically, the label house is a label to some feelings, to some internal representations that we have for some kind of events, but they cannot be represented in an image. So basically, there's a context behind a label, and that context is lost. Or even if you say, okay, so I provide a caption for the image so that I encode the context in itself as well, but it's even not very easy. For instance, this image is showing the context of like, if you don't know the caption, you can guess a lot of context for this image, but the caption is a hot blonde girl getting criticized by her boss, and you put this in your training data and you train your model, but then the model is biased towards learning some contexts that are not relevant everywhere, and it's hard to actually judge whether they are true or not based on different environments that you're looking at the data. So basically, it's important to have something that captures the context inside the environment itself. So if you take something out of the environment as a sample and then train some models in different environments based on the samples that you got in other environments, I think you may get some unnecessarily extra biases. So labels or captions can ignore the context. So after that, people came up and tried to think about how we can solve these problems, and one solution that we have now come up with and we're trying to push is self-supervised learning. In self-supervised learning, you're trying to create labels using only data, so you don't need to extract any label, or you don't need to manually add label to your data. And how it works is that you have a pre-training phase, you have unlabeled data, and you try to create labels using the data. For instance, you can define some transformations like rotate, which gets the input x and a degree, and rotates that input by that degree. And then you train a deep neural network to predict the degree of the rotation of your input. For instance, you get your input, you rotate it by 90 degree, by 180 degree, and then you pass it to the deep neural network, and the deep neural network should predict the amount of rotation as a task. So it's a simple classification task, and we call it a proxy task. And through this, we hope that we learn some high-level features, some useful features that can be employed for the downstream task to learn much faster from the downstream task data set. So here, for the downstream task data set, we use much less labeled data. For instance, I don't know, 1,000 times or 100 times less data compared to the unlabeled data. And because the deep neural network has been trained to learn some high-level features in the pre-training phase, it now can employ those learned high-level features, which are hopefully good, to learn much faster compared to the situation where you need to train everything from scratch, starting from Gaussian random weights. So this is the concept that people in self-supervised learning try to push for. They try to learn some general prior features, let's say, so that they can be easily used in between domains, and you can employ them for different tasks to learn faster with less amount of data. So what makes self-supervised learning effective? First of all, it needs no supervision, which results in massive scale, which results in learning general priors because we have much more data, which results in capturing key data features and transferring better to other domains. We have created a lot of models with this approach with different loss functions, of course, such as GPT, Dino, MAE, or Dino version 2, and they have been shown to be very effective in different domains. For instance, if you directly use these features that have been learned, let's say, through these SSL methods like Dino version 2, and if you combine them with stable diffusion features for other domains like, I don't know, semantic correspondence or some specific tasks like point correspondence, it has been shown that the combination of Dino version 2 features and stable diffusion features provide state-of-the-art results, and they are somehow complementary to each other. So the priors that are learned through self-supervised learning methods, because they are general, they are capturing some key aspects of the features that may not be captured specifically with some supervised tasks or some specifically designed models. And therefore, you can just use them as just on-the-shelf models to improve your performance. Again, there are some research showing that for vision language models, basically you have nowadays in vision language models, for instance, for Lava, people use clip encoder and some text encoder, and simply they try to align them with through an adapter network, adapting the clip vision encoder features to the large language model feature space, and then they try to create a vision language model for multimodal training. But this is prone to hallucination, and as all of you know, may get stuck in the suboptimal position. So basically they try to improve this hallucination problem by adding Dino features to the clip features and then aligning them to the large language model space, and it has been shown to be effective by improving the hallucination rate of Lava backbone by 10% or something like that. So the frozen features learned through self-supervised learning methods actually add some information to the models that you learn through weakly supervised training or supervised training. So the question now is, how can we learn more real-world priors? Because Dino version 2 is good because it seems to be close to real-world priors, or it can reduce hallucination rate of clip version 2 because it has learned something that doesn't exist in the clip architecture. But now we want to even push these priors further to learn better priors. And the question is how? And we think that videos open exciting new directions. Videos can be used for visual development. For instance, you may guess something about your model at the beginning. For instance, you may say that, okay, this is the person is doing something, but when the time passes by, you realize that, oh, your judgment might be false or might be true. So this helps you to basically edit your features that you learn through the process. It helps you to understand the physics of the world, of course, the interactions of objects with each other, just like a human being can help us to learn physics. And also, of course, I think for embodied AI, you want to have a robot doing some tasks, and it's important to be able to learn from the video signals that the robot is receiving. And also pointing out what LeCun said, basically I'm not going through the math, but he's saying that even the largest large language model has seen 15 times less information compared to a 4-year old child, which means that the way that we are trying to design supervised training or weakly supervised training is still not as scalable as how human being is collecting data. And scalability is important, so we need to come up with new solutions to learn from data, which is different from images or supervised training or weakly supervised training. And here are some examples of how videos and images are different. If you look at these images, if you look at only the first frame, you may think that these guys have a very huge height difference, but it's just an illusion. And by watching the video, you would realize that okay, maybe something else is different in this room, and these guys are not do not have a huge height difference compared to each other. So this is where you need to watch a video actually to understand the scene. Also a similar example here. So the height difference is not that much real, and by just watching the video you may realize that okay, there might be some other underlying factors going on here. Also, this interesting example, the color of points A and B are exactly similar, but through watching video you realize if you only look at the last frame, you may think that A and B are not similar, but actually they are similar, and only through watching video you may realize that okay, your brain is just processing some information to make B a bit more fade compared to A, and that's how you understand about what's going on here.